Wonderful. Okay, welcome to the 2020 Summer Colloquium. It's my pleasure to be the host for this annual event because I am the managing director, the overall managing director of our institute, the Max Planck Institute for Intelligent Systems. Normally, this event is held in a live format in our large auditorium on the Stuttgart campus. Here are some pictures from our event last year where we had 3 great speakers and the prize winner, and it was truly a lovely event. You see people sitting close together and not wearing masks and enjoying great science on a Friday afternoon, learning about intelligent systems. And of course, that was 2019, and this is 2020. And it's a year, I think, unlike any other that we've ever experienced here in the Institute or perhaps anywhere in the world due to the coronavirus, this novel coronavirus, COVID-19. But I'm really proud of how our Institute has continued to work, continued to do research, continued to band together as a team despite the challenges that our society is facing, these health challenges, this pandemic, and all the changes those have wreaked upon our lives. So today we decided to, instead of holding the event live or in person, which wasn't really feasible, an event of this scale, we decided to hold it in a virtual format. And I'm really pleased to be able to deliver this event to you today as the sort of master of ceremonies. We have a great lineup of 4 scientific talks, one of which is the winner of our 2020 Günter Petzow Prize. And then new this year, the last piece is a Ph.D. graduation ceremony where we'll be honoring 16 people from our institute who have finished their doctoral thesis in the last year. We've never done an event virtually of this scale, so I ask you for your patience and understanding. Any live event, things go wrong, and so we'll just do our best to adapt and stick with us, and I'm really, so we'll do our best, and thank you everyone for joining us today. Before we start with the first talk, my job as host is to share a little bit about the logistics for this event and then give you an overview of our institute, just so you can place this event in your mind and kind of understand where we're coming from. So we have 2 ways in which people are participating today. Well, kind of 3 actually. We have a Zoom webinar running, and we have live panelists, people who will be speaking, leaders in our institute and organizers, and then a lot of people who've joined the Zoom webinar as just guests. They can't turn their camera on, but they can see and they can add questions in the Q&A. Here in the Zoom webinar, you had to register in advance so we know the community. And you also have to give consent to be recorded, but that's only if you unmute yourself and have your the panelists, they have their camera on. You won't be recorded if you don't say anything. If you're here in the Zoom webinar, you'll be able to see the whole program, all 4 talks plus the PhD graduation ceremony, 1 live streaming broadcast, all back to back to back to back. And you can participate a little bit more interactively by asking questions. You can type questions in the Q&A panel. We prefer you don't send them in the chat because the Q&A, it's easier for other people to see and upvote your questions. And then also it's possible for you to raise your hand virtually once we get to that point in the program. And we can unmute you, but I think we'll probably mainly stick with the Q&A and also the other people on the panel asking questions verbally to have it a little bit more like a real seminar, a real conference, a real workshop. And then we also have a whole bunch of other viewers, not in Zoom, but on YouTube watching the live stream. There's a little bit of a delay, maybe 10, 15 seconds, but they're going to be able to catch and see everything we're doing and saying here. It's visible. You can go to our Institute website, find the event page and just watch live there, or go to our channel, our Institute's channel on YouTube. Here, if you're watching the live stream, you're going to see 2 separate parts. The first part, and then we'll pause it because Marco Hutter, one of our speakers, is presenting some work that's not published, so we don't want to create an archival record of that. So you have to be in the Zoom. If you want to see Marco Hutter's talk, you can still register for the webinar and you can still join, but that just means we have your contact information. And there isn't an opportunity to ask questions live, but of course you can write to any of the speakers, send them an email. I'm sure they would love to hear from you about your interest in their research afterward through other channels. And we plan to archive the live stream recording online, barring any technical challenges or other issues that arise, but we hope that will also serve as a nice long-term record. So that's it for logistics, and then I'll move into just a brief overview about our institute. The world is large. We're here in Germany, in Europe, and that is not how that's supposed to look, but there would be a map of Germany there, and it would show you that we're in the southern Germany. We're in southern Germany. You can see it. No, can't see it. So we'll just keep going. Our institute is in southern Germany, in Stuttgart and Tübingen, which are two cities in Baden-Württemberg. And we were founded in 2011, these two sites in Stuttgart and Tübingen. There are over 80 institutes, Max Planck Institutes around the world, mainly in Germany, and they are focused on all different scientific topics. Our institute in particular centers on intelligent systems. And by this, we mean both living and artificial creatures, algorithms, robots, devices that can interact with the complexity that's found in the real world. So we both focus on the science of intelligent systems to understand the fundamental principles of intelligent systems, which we often talk about being perception, action, and learning. And then we use those insights to create new future systems. As I already alluded to, our site in Stuttgart, where I am today, is a bit more focused on physical systems. And in Tübingen, you see our beautiful, relatively new building in Tübingen, where I think several of the panelists are located. It's more of a focus on computational. This isn't a clean divide. There's a lot of overlap and connection, and we really try to build on the strengths of both of these two locations and the connections they have each to their local universities in Stuttgart and Tübingen. And we have quite diverse research and aspire to be the best international center in this work, in this area, doing everything from algorithms to physical implementation, learning, inference, vision, control, robotics, and haptics. I chose just 9 quick images to give you a fast flavor of the range and type of research our people are engaged in. And now I'm going to go ahead and introduce our scientific leaders to you, those of the ones who are on the Zoom webinar and also those who weren't able to make it. Along the top, we'll start with our directors, and I'll just ask if any of you are here, please just unmute and introduce yourself. So starting at the far left, is Michael Black here?
That would be me. Yes, I'm here. I'm located in Tübingen. I head the Perceiving Systems Department, and my main interests are in computer vision and particularly using computers to understand how people move.
Thank you, Michael. Next, Bernhard.
Hello, Bernhard Schökopf. I'm the head of the Empirical Inference Department. So empirical inference stands for inference performed based on data. So we think it's a crucial component of intelligence in different forms. This inference could be machine learning, and much of what we do is machine learning, but there are also other forms of inference, and causal inference is such an example, and we're working in these domains and also trying to bring together machine learning and causality to address what we think are the open problems in the field. So, based in Tübingen also.
Thank you, Bernhard. Both Michael and Bernhard were founding directors of our institute, so they've been here the longest. I'm Katherine Kuchenbecker. I'm a director here in the Stuttgart site, and my research centers on haptics, which has to do with the sense of touch, both fundamentally understanding contact interactions, endowing robots with a sense of touch, creating compelling haptic stimuli for human users, and also doing human-robot interaction. So next, Metin.
Hi everyone, I am Metin Siti. I'm heading Physical Intelligence Department in our Stuttgart site. My group focuses on fundamental understanding of intelligence in the sense of physical aspects like the body intelligence, how materials and mechanisms and other aspects of the physical system make our systems more intelligent in addition to brain. And also we work on especially small-scale mobile robots for medical applications.
Cool, thanks. Metin joined the Institute in 2014. He was the first director in the new direction in Stuttgart. We also are lucky to have 2 directors who were previously in the Metallforschung, metals research, that was the previous focus of our institute. Professor Dietrich, his department is called Theory of Inhomogeneous Condensed Matter. He's a theoretician, a physicist. I don't think he's here today. And then last but not least, Gisela.
Yeah, Leschitz. I am head of the Department of Modern Magnetic Systems. I am here since 2000. This means 11 years in Metallforschung and 9 years already in intelligent systems.
Great, thank you all so much for joining. I also want to remind everyone we are hoping, or quite soon, to welcome a new director here in Stuttgart. The planned start date is August 1st, a week from tomorrow. So fingers crossed that everything works and we'll have a big announcement soon. We're also working on hiring a new director in Tübingen, but that one is a little bit farther behind in the process, but hopefully we'll have a good announcement there as well, filling out the intelligent systems direction. Now we move to our group leaders. So whereas directors are appointed as like a tenured full professor with employment until they're retired, group leaders are almost all a shorter term appointment and more like a tenure track assistant or associate professor. And they're really the vibrant spirit of our group, of our institute. And so we'll just start here at the bottom left and go across. So these are alphabetical order. Is Katherine here? I don't think so. So Katherine de Bacco is a Cyber Valley group leader who joined in 2018, and her group is called Physics for Inference and Optimization. Is Andreas here? Andreas was a Max Planck group leader in our Tübingen site. Katherine is also in Tübingen, and Andreas is already a professor at the University of Tübingen. His group is on autonomous vision. Is Falk here? Falk leader is also a Cyber Valley group leader who joined in 2018, and his group is on rationality enhancement. Georg.
Yes, I'm here. I'm Georg Motzius. I'm a group leader in Tübingen. My group is called Autonomous Learning, and we work on machine learning for robotics. We would like to make robots that can work, that can learn a little bit more like children. And so we are working on trying to get the most of machine learning into this world.
Cool. Thank you, Georg. Ludovic Rigetti, I don't think is here. He's a group leader in our Tübingen site. He's also a tenure track professor at NYU in the USA. Jörg Stückler is a Cyber Valley group leader in Tübingen. His group is Embodied Vision. Isabel Valera is a Max Planck group leader. Her group is called Probabilistic Learning, and she'll soon be taking a W3 professor position at the University of Saarland. Alexander?
Yeah, hello, I'm Alexander Batrisch-Privitz. I'm leading the dynamic locomotion group here in Stuttgart. I'm interested in all aspects of legged locomotion, and especially we're looking at animals and also machines.
Super, and you can see we have quite a few talks related to locomotion in our colloquium today. Per?
Yeah, hello, my name is Per Fischer. I head the Micro, Nano and Molecular Systems lab. It's sort of systems at the very smallest of scales, and I'm also a professor of physical engineering, chemistry in the University of Stuttgart.
Great, yeah, and Per is, of our group leaders, the only one who has a permanent position, so he's been here since the start of the institute. Ardian?
Hello, my name is Ardian Yusufi. I lead the lab for locomotion in biorobotic and somatic systems in Stuttgart. We are interested in the neuromechanics of how animals move and in implement that for more robust locomotion in robots.
Thanks, Ardian. Ardian's another one of our 5 Cyber Valley group leaders. I don't know if Lara is here. She's been a group leader in our institute since it was Metallforschung, and her group is Smart Nanoplasmonics. And last but not least, Sebastian Trimpe is a Cyber Valley group leader in Stuttgart. His group is Intelligent Control Systems, and he has already started as a W3 professor in Aachen. And so because you heard me mention 3 of our group leaders have already taken professor positions, this is the best thing that we wish for them. We do have these 3 open group leader positions, and you'll be hearing more from the institute in the coming months as we go through the process of trying to find really great new younger early career PIs to fill these 3 groups. We also have 2 Max Planck fellows in Tübingen. I don't know if they're here. I think Ulrike von Luxberg is a professor at the University of Tübingen. Her group in our institute is Statistical Learning Theory. And here in Stuttgart, it's Marc Toussaint from the University of Stuttgart, and his team is Physical Reasoning and Manipulation. Marc recently took a position at TU Berlin, and so his Max Planck Fellow position will also be open in the coming years, but he's still working in our institute for now. All right, so that was the scientific leaders. I also want to take a moment to acknowledge all the people and teams who support our research, and these are our central services. Alina and Matthias are key to the whole flourishing of our institute. Alina, would you mind? And then Matthias, quickly introducing yourselves.
My name is Aline Dietrich. I'm head of administration in MPIIS.
Super. Yeah, and Alina joined our institute in September of last year and has really done an amazing job building up our own administration. It used to be shared with another institute here in Stuttgart, and now I'm really grateful to all the work Alina and her team is doing. And Matthias?
Hi, I'm Matthias Tröntle. I'm leading the scientific coordination office, and we're taking care of communication, events, grants, building coordination, and so on. So supporting the science that is going on in our institute.
Great, and I really deeply appreciate all the work they both do. And then we have IT groups and building services in both sites, as well as a really key aspect of Max Planck Institute's our central scientific facilities, sometimes called ZVAs. And there are 3 in each of our 2 sites. And we'll just go from the left. We have a scientific computing ZVA. Are Jojoman or Joanne here? So those are the 2, these are all PhD holding scientists who help lead the team. We have an optics and sensing lab in Tübingen. Are Valentin and Orsenia here? Okay. A software workshop also in Tübingen. Jean-Claude?
Yes, I'm here. Hi. So I'm Jean-Claude Passy. I'm leading the software workshop located in Tübingen. And we are currently 2 full-time scientists there, myself and Ivan.
Oh,
and
sorry, I should have added Ivan, my bad.
Oh, good. And so our goal is to support the software development and institute in any way we can.
Well, thank you. All right, and then we move to Stuttgart and the robotics ZVA. Jonathan?
Hello, I'm Jonathan Feeney, leading the robotics ZVA in Stuttgart, where we're working to design and prototype different mechatronic and robotic systems for researchers around the institute.
Thank you. Then we have a materials ZVA. Günter?
Hello, my name is Günter Richter. I'm heading the materials lab. Our service is to provide via thin film deposition specimens. We have some basic analysis tools like SEM and X-ray diffraction, and my scientific interest to explore the size effects of physical properties in model systems.
Super. And then lastly, we have a medical systems ZVA that's also in Stuttgart, and Yelena Zanati is one of the PhD holding scientists there. I want to just take a moment to thank all these administrative, scientific coordination, IT, building services, and ZVA staff for all that they do to enable the research in our institute. We couldn't do what we're doing without you, especially during these difficult times. Thank you, and keep up the good work. This is the end of my institute introduction. I wanted to close with a picture from our retreat last year where we were allowed to stand close together without wearing masks. And I'm sure we're headed back in that direction, but I'm really proud of our spirit of not giving up and continuing to hold this event, even in this different format, in this virtual event. So now we move to the actual program. And like I said, we have 4 talks back to back. And the first will be given by Professor Syn Schmitt. Syn is a professor at the University of Stuttgart. He is a physicist by training. And I think at this point, everyone who's, I forgot to say, everyone who was just a member of our leadership, you're welcome to leave or leave the panel. If you want to stay to be able to ask questions during Syn's talk and the other talks, you're welcome to stay, but you don't have to. So back to my introduction of Syn. Syn is a physicist by training, and he actually earned his first degrees at the University of Stuttgart, so right by our institute, and then he got his PhD in the University of Tübingen. So we could say he's Cyber Valley through and through, where he studied theoretical astrophysics, but mainly muscle modeling. And then he started his faculty career in 2012 as a junior professor and assistant professor at the University of Stuttgart. He earned tenure as a full professor in 2018 and co-founded a new institute in 2019 on modeling and simulation of biomechanical systems. He has a big role in SimTech, which is one of the excellence clusters, a very famous, big and successful excellence cluster at the University of Stuttgart. And he's also a faculty member in our International Max Planck Research School for Intelligent Systems, which is joint with the University of Stuttgart and the University of Tübingen. And so I'm really delighted that Syn accepted our invitation to speak today so that we could all learn about his interesting research. And I'll go ahead and stop sharing so that Syn can start sharing his slides.
Now I'm sharing my slides. Can you see them?
Yes, I see them.
But not in full screen, unfortunately.
Not quite in full screen mode.
Yeah, I'm not sure why, but trying to find it out. View full screen. Okay. Should work now, right? Okay, thank you very much for the kind introduction, Katherine, and Metin and Katherine for the invitation. I feel very honored to present my research today. And first of all, I'd like to give credits to my co-workers and my fantastic group, because most of the research I present today, of course, is the result of their research. And I would want to especially mention today two people who are fantastic collaborators and researchers. This is Daniel Häufle from the Hertie Institute of Tübingen and Kian Ghazi Zahedi, formerly with the MPI of Mathematics and unfortunately left academia. Both of them were collaborators in the field of morphological intelligence. And that's a talk I'm going to present today. And as you might have seen, I've changed the title a slightly bit just to integrate learning as well. Today, I'm going to tell a story about the brain and its communication with the body. But because I cannot really understand the brain, I simply don't speak its language, I rather trying to look at the body and see whether I can learn something of the communication between brain and body. So let's start with the brain. This video, I hope it works, yeah. This video shows a picture, a data set of a human 3D neuroanatomy of a brain. It was a 58-year-old woman. She died of non-neurological causes and had no history of neurological disease. The brain was fixed in formalin 14 hours after death, and it took over 100 hours of scan time. I think this gives a fantastic insight into the brain's anatomy. And there's no doubt that the brain is one of the single most powerful organs in nature. This picture depicts the brain of Albert Einstein. It was also fixed in formalin shortly after his death. And with Einstein, we clearly associate a bright mind, a genius, unmatched brain power or intelligence. And the brain seems to be everything of a person, although typical brains make up only 2% of the body weight. It contains about 86 billion nerve cells, the gray matter, billions of nerve fibers, which is the white matter, and trillions of connections, the synapses. And it consumes approximately 20% of total metabolic energy. And I'm sure Peter Dayan will disclose many more fascinating things about the brain in the next talk. So brain, bright mind, intelligence, these words are used as synonyms. Now I show you some tasks in which I think the brain is heavily involved as well. On the top left, you see Usain Bolt, the fastest man on earth. He's able to accelerate within 60 meters to a top speed of 44 kilometers an hour. Or in the top right, Lang Lang, the piano player, he hits the keys in fast parts of a song for 30 times a second, which means 400 to 600 muscle excitations in 1 second. Or the top left, Michael van Gerwen, world champion in darts match play, he repetitively hit bullseye, 12 millimeters diameter in 2.5 meters away from bullseye. Or on the bottom right, Dean Potter, my, let's say, most favorite human motion, he's able to balance on a rope 30 meters long, 1,000 meters above ground at Taft Point, the Yosemite Valley. Now I ask, do we call these guys intelligent? Well, maybe, but most people would describe their outstanding capabilities rather with gifted, trained, or experienced. Why not intelligent? Maybe because it's a different type of intelligence. Maybe because the brain is not so much involved as initially thought it would be. But is biological motion at all possible without the brain being involved? Well, in technical systems, there exists a concept for 30 years now, the passive dynamic walking concept, found by Ted McGeer. This is a more recent example of such a walker. It describes self-propelled legged walking on an inclined plane. The system moves without any external or internal control, purely exploiting its structure and the interaction with the environment. This concept and similar research coined the term intelligence by mechanics or morphological computation. Although people argue that in the latter example of the passive walker, no computation is done at all. that's one of the reasons I broadened the title a bit to morphological intelligence. So for this movement and this structure and this environment, no brain is needed. Thus, it seems that a perfectly adapted structure facilitates or even presets a specific behavior in a specific environment. And that brings us back to biological or natural systems. No other known process has proved to force adaptation more than the evolution of biological systems. And I call these systems natural intelligence systems. And that is the bigger picture of my research. As already mentioned, intelligence is somewhat undefined or vaguely defined. And one quite practical definition is that of David Krakauer, who says, intelligence is making hard problems easy. Or another one is from Robert Brooks, the source of intelligence is not only limited to the computational engine. Or you, the MPI for intelligent systems, define intelligent systems as systems which operate autonomously in and adapt to complex changing environments. Now, taking the morphology into consideration, one could say morphological intelligence is the reduction of computational cost for the brain or controller, resulting from the exploitation of the morphology and its interaction with the environment, according to Kian. And this brings me to my main question: how much contributes the system design to motion and thus helps the brain? And with system design, I mean the structures of the topology and material characteristics. In literature, there are many indications that morphology is instrumental and auxiliary for observed biological motions. For example, reduced oscillations in the actuation system by inherent small viscous damping, increased stability by agonist-antagonistic pairs of muscles around the joint, or simplified control, for example, in ground contact by soft tissue dynamics, or energy storage and recovery in a step cycle. Now, our question is, how much does the design contribute? Which structure and or characteristics? Can we compare different systems performing the same motion to evaluate their differences quantitatively? Again, quite many measures exist, like movement speed, energy cost, control stability, minimum attention control. But as soon as you want to apply them, you realize that different systems have different designs, for example, actuation principles. In a humanoid robot, for example, we're able to measure motor voltage in volt, motor torque in Newton meters, or pressure in kilopascal. In a biological system, you can observe muscle EMG, again in volt, or muscle activity, reflex activation. So these are all signals which were proposed to assess individual systems properly, but how to compare between systems or between different actuation principles. And I will present you today two relatively new measures to evaluate the contributions and different actuation principles. We will talk about control effort and morphological computation as measures. We'll apply them to hopping, to smaller scale, so more micro swimmer scale, and more complex motion, pointing and walking. And the last example will be on learning and how morphology contributes here. So let's start with the first measure, control effort. This approach is based on the cybernetic analogy between humans and machines, describing both as control systems. To achieve a goal, both use sensors to take measurements of their state and the environment, transmit and process the gathered information, and take actions accordingly. According to Shannon, the prior uncertainty of the outcome when measuring the variable u can be quantified as the entropy of an information source, where p is the probability of the specific sensor measurement result u. Let us consider a linear sensor measuring a state variable u of a system. The sensor has then a range u min to u max, as depicted on the right-hand side, and a resolution delta u, and thus n equals 1 plus u max minus u min divided by delta u. Possible measurement results. And after some math, we'll skip over, and simplification, the total information processed for a typical sensor is then, as shown here, I equals capital T divided by delta T log 2, and then 1 plus u max minus u min divided by delta u. And this equation can be applied to almost any type of sensor. It requires only a discretized sensor output and finite number of repeated measurements. The information can then be determined from the duration of the movement, capital T, and the time resolution delta T, and the sensor properties. To determine control effort for a fair comparison of different systems, we have to apply it in 3 different steps. And I'd like to explain those 3 steps now on the example of hopping. So the first step is to define a movement and a performance criteria of this movement. We chose human hopping because it's relatively easy to define. You have a ground clearance and some performance reduction if the frequency is less than a certain barrier. Step 2 is then to generate a movement with different models. You want to compare different morphologies, for example, or different control concepts or actuation principles. Here we chose feedback, feed-forward, or PD controller. And the third step is then to search the minimum information necessary to generate this motion. That means that you have to define a performance corridor, and then delta U and delta T have to be varied until the minimum of I is reached while maintaining the defined performance. And then I min equals the control effort, so the minimal information needed to perform this motion. And for our example of human hopping, we found that the control effort is minimal for muscle actuation and feedback and feed forward. I min is 32 bits. Compared to a DC motor driven system with PD controller, where the control effort is 20 times higher. So the amount of information processed to perform this given task is minimal for muscle driven feedback systems in hopping. And in general terms, I would say higher morphological intelligence for muscle driven systems can be seen. Now I stay with hopping, but we'll use a different measure to evaluate the contribution of the system design to motion. And this measure was developed by Dayan from MPI for mathematics in Leipzig. It starts with a causal model of the sensory motor loop depicted on the left-hand side and acknowledge that a cognitive system is embedded in an environment, as shown here, and cannot be understood detached from it. So this measure is trying to isolate how much the current world state W, as you can see in the middle, influences the next world state W prime. And the world dynamics kernel alpha then captures the influence of the actuator signal A and the previous world state W in the next world state. A complete lack of morphological computation here would mean that the behavior of the system is entirely determined by the system's controller and hence by the actuator state. And in this case, the world dynamics kernel reduces to the probability P of W prime given A. So every difference from this assumption means that the previous world state W had an influence, and hence the information about W changes the distribution over the next world state W prime. And with this, and by comparing the two distributions, we can measure the contribution to morphological computation. And we used similar models as shown in the hopping example for control effort. Again, DC motor, muscle-driven system. And for the muscle-driven system, we use one linear muscle model and one more biologic-like nonlinear one, and compare them and analyze and calculate morphological computation. And we found, you see here on the right-hand side, the position of the mass on the bottom, and below 1 meter, the mass touches the ground, and above 1 meter, it's in the air. So during flight phase, all 3 models do not really separate. So morphological computation is high and almost the same. But in ground contact, the bio-like nonlinear muscle-driven model separates from the other 2, and morphological computation is high in exactly that phase. And that was expected by us before. So again, with this measure, we can show that higher morphological intelligence for muscle-driven systems can be seen in this example using this measure. Now we switch to much smaller systems, microswimmer. Now, the motion of active microswimmers is characterized by a combination of directed, deterministic, and stochastic motion. In spherical microswimmers, the active propulsion leads to linear velocities. By exploiting their random reorientation, it is possible to steer them towards targets. An active propulsion of asymmetric L-shaped particles leads to circular or untilted substrates, then to directed motion. So with this, you can steer them. Thus, the difference in shape or morphology influences the motion. And with specific control schemes, we try to it's possible to steer them, and we try to steer them in circles and along lines towards targets. And as the different morphologies influence the control, we assess the control schemes by evaluating their control effort. That is the amount of information required to steer the particles. And we compared that in computer simulations. So two different Janus particles, the J, capital J and small j Janus particles, and one L-shaped particle. And for one L-shaped particle, we compared 3 different types of motion, 3 different types of radii. One which is typical for this L shape, and a very small one and a very large radius. And we can show with this research that the control effort depends on the morphology and on the task. In the middle, you see information calculated, so again, control effort, the top graph in the middle, which shows that for L-shaped particles, the green one is lowest for a comparison between the particles. And on the right-hand side, you see that in red, that the movement of a typical L-shaped particle in a typical radius is also lowest. So control effort is lowest here, as we have expected. So again, we see higher morphological intelligence for bio-like structures. And that brings me then back to the macroscopic world. And the question is here whether this metric holds also for more complex motion. So not only for hopping or for very small motion, but also for pointing tasks, aperiodic ones, or for walking. And the key idea is to compare, say, the same movement, but generated by different actuators. So one torque-driven pointing task and a torque-driven walking. And the hypothesis was that the muscle characteristics simplify control because less information is required. And we used, again, information entropy, so control effort, to measure the contribution of the morphology to the motion. And to find a minimum information process, we coarsened the resolution, both the amplitude and the time resolution. And the coarsest resolution then is where the movement still works, but with minimal information. And this is then control effort. And as results, you see that in the pointing motion for stim and sense, both the bio-like actuation, control effort is lower compared to the torque activation. And this holds also for walking, where stim and sense is lower compared to torque. So our results show that muscle-driven systems require less information to generate a movement. So muscle reduce neural information load. And in a broader sense, we see higher morphological intelligence for bio-like actuators. And my last example now leaves the field of direct movement control and deals with the question how simple a control task can be learned when exploiting the morphology, or vice versa. How does morphology facilitate learning? For this to study, we simulated pointing and cyclic hand-arm movement and used a hand-arm robot from our lab with muscle-like pneumatic actuators. And by adjusting stimulation values in the muscle-driven computational model or pressure values for the pneumatic actuators, we were able to reach a certain end effector point in space. So with only one initial given point, which is initial data set, and a predefined strategy to explore other stimulation patterns, the goal was then to learn a control policy as the function pi, which maps the desired hand position, xref, to normalized muscle stimulation or pressure values. And due to the structure of the biological system, each constant muscle stimulation U shifts the equilibrium to a new position, which allowed us to bootstrap and learn a forward model from the growing data set. And the results turned out to be very good, not only in the movement performance, what you can see on the top right, for point reaching evaluation in the simulator, we were able to reach the points with an error of 1 millimeter roughly, and circle trajectory following on the right. For the robotic system, the error was a little bit higher, it was about 4 to 8 millimeters due to hysteresis in the mechanical design. But not only the movement performance was high, also the learning performance. We compared that to, and this was done in Marc Toussaint's lab, compared that to other learning methods like distal teacher, weighting, and saw that we had a persistently lower evaluation error and a very small number of data points needed to learn the motion. So again, from the perspective of this talk, morphological intelligence facilitates learning. Now, to sum up, we talked about intelligence, mostly associated with tasks of the brain, especially thoughts and reasoning, and less or mostly not with motion. We found biological motion to be tremendously complex and hypothesized that heavy brain involvement. Additionally, we hypothesized that natural intelligence systems make use of the morphology and material characteristics to successfully behave in a given environment. We asked how much the design contributes to motion, control, and learning. And I introduced you two relatively new measures: control effort, developed by Daniel Häufle during his PhD, and morphological computation, developed by Kian Gaisi-Zahedi. And we applied that to different motions, a very simple one, hopping, to microstructures like the micro swimmer, or to more complex motion like pointing and walking. And we even then looked into learning tasks and saw that morphology facilitates learning as well. So I showed you this argumentation, and I hope that you are now a bit convinced. But of course, not all is done by the brain. That's, let's say, the basic message here. Despite its powerful capabilities, but still the brain is crucial, and especially for very complex movements like this one. And with this, oh, sorry. And with this, I'd like to thank you, and I hope there are some questions.
Thank you so much, Syn, for this beautiful and very compelling presentation. I'd like to first invite questions from the other people here in the panelists. Maybe Georg has a question, or Per. Please go ahead, Georg.
Yeah, very nice. Thanks a lot, Syn, for this interesting talk. As a matter of fact, I was sitting next to Kian for a couple of years in my career, so I know him very well. I'm very happy to see this carried on. And I was wondering, so in this first part, you essentially computed the information as from the discretization of the space into equal buckets, and then you even had this equal probability on them. Did you also try to estimate the probabilities really from the empirical distribution and really compute the entropies, which would be too difficult? Is there a different result to be expected, or?
No, actually, we haven't tried it. We're still trying to find out whether it's better to discretize the sensory input or the motor output here. Mm-hmm. So we're still at a very basic stage and that's why I showed in the pointing and walking both stim and sense as the source of the minimal information. So we're still not decided what the best signal here is. So no, we didn't really go into the entropy calculation.
Mm-hmm.
Great. Who would like to ask the next question?
Yeah, maybe I can appear here. So very nice talk, very general. I think that's always the beauty if one can see the connection between such different systems on different scales. For the very small ones, which are close to my heart, I wonder, the control parameters are usually very limited. So I was wondering what was the control parameter or the external force that you actually could change? And then maybe related to this is, and the question that I think always comes up is whether one can even have learning in such systems, or whether that then becomes impossible for physiological or technical reasons, because several of these systems don't possess anything like a brain.
Mm-hmm. Thank you, Per, for this challenging question. I think I can't answer neither of both. So the first one is, okay, we try to adapt the force levels with which you can control and steer the microparticles to what in experiments is done. So for example, from Clemens Bechinger's lab. So we did that in computer simulation. together with Christian Holm from the computer physics department. But I'm not really sure how high the forces are, so I would have to look that up. Sorry for that. But the second one is, yeah, we think that learning could be used, maybe not in the micro swimmer, but rather on the controller side. So, for example, if you turn the light on or off, with which you actually steer them, there you can maybe use learning as soon as you can recognize where the particle really is. I think that was the challenging part in the experiments. Yeah, but then could be possible.
And I think that is possible in Clemens's type of experiment.
Yeah.
Well, I think we have time for one final question. Alexander?
I have a...
Yeah, let me, okay, we'll do two, but Alexander and then Ardian. I'm just going in the order people showed their videos. So Alexander and then Ardian.
Yeah, it's a very, very nice talk. Thanks a lot. So you're showing that your muscle-based system have a lower information load and a higher morphological computation, and clearly that there must have been an evolutionary pressure which was leading to that scenario what we see nowadays. Do you think there's an actual advantage if we do compare them nowadays to the robotic applications to mimic that, or do you also see disadvantages of something like that, or should we just try to make smarter actuators?
Well, it's always better to make smarter actuators in my perspective, but yes, I think that measure can be used to compare systems and also maybe to see how close or even better than human performance you are in terms of morphological intelligence. So how intelligent, how ingenious your design is in terms of morphology, the body structure, compared to human performance. Yeah.
Super. And we'll just have one last question by Ardian. Go ahead.
Hello, brilliant talk, Syn. I have a question on the control effort reduced to various types of responses. So can you comment on reflexes versus preflexes? So for bandwidth limited tasks, we know, for example, that insects can run something like 30 body lengths per second, and there is not that much time for sensory feedback to change and respond to perturbations. So with these preflexes, they can reject obstacles up to 3 times hip height and run unperturbed, essentially, in a very rough terrain. So how would we quantify the control effort reduced in preflexes versus traditional reflexes as we know them in the somatic nervous system?
Thank you for this question. This is exactly what I said for the question of, I think it was Per, that we actually, no, it was from Georg. I think this is actually the type of, or the status at which we are currently, to try out whether it's better to calculate control effort on the sensory side, where you capture the whole sensory information, or on the controller side. If you calculate it on the controller side, then you have all the preflex pre-wiring already included, while for the sensory information, maybe a control effort would be much higher. So I think with this, you could compare it. And it would be even better to use morphological computation as introduced by Kian, because then you can say what is coming directly from sensors and from which type of sensors, and what type of information, or the quantity of information which is coming from the actuators.
Thank you very much.
Thank you, Ardian, and the other people who asked questions. Let's thank Syn again for his beautiful talk, and it's so nice to have a chance to learn about your interesting research. So we'll go ahead and move to the second scientific talk. I don't need to show any of my slides. I'll just do the introduction while our speaker goes ahead and shares his screen. So our second presenter is Dr. Peter Dayan. He is a mathematician by training, where he read mathematics in Cambridge and did his PhD at Edinburgh, did postdocs with a few different people, including Jeff Hinton in Toronto. He started his independent scientific career at MIT in the Department of Brain and Cognitive Sciences, and then moved to University of College London, where he founded the very famous now Gatsby Computational Neuroscience Unit, which he ran for 15 years. And it was really a coup for the Max Planck Society and the University of Tübingen and the Tübingen region, Baden-Württemberg, to convince him to move to Tübingen to become a director at the Max Planck Institute for Biological Cybernetics a couple years ago. So he'll be telling us about some of his research today. I'll also mention he's a member of the associated faculty for our International Max Planck Research School on Intelligent Systems. Please join me in welcoming Peter Dayan.
Thank you very much indeed. It's a great pleasure to be here. Really grateful for the invitation. I hope that my talk is not a move from the sublime of that beautiful dancer to the ridiculous of the small task that you'll see that I'm going to talk about. So the work I'm going to talk about is joint with, particularly with Rani Moran, who's a postdoc with Ray Dolan and myself in London. So really it's a tale of two Edwards. This is Edward Thorndike, who actually turned out to have been a classmate in a class taught by William James with Gertrude Stein, very interesting, a conjunction of people together in Harvard. So Thorndike is famous for a sort of learning task in which here you have a cat in a little box. The cats don't like to be confined in the box. And there's an action they can do. They can like press a treadle or move a lever to get out of the box. And what you see is the course of learning. So here over many trials, so this is up to 70 trials, this is the time that it takes the cat to leave the box. And so what Thorndike was interested in is the idea that the animals, of course, they perform an action and they learn progressively to get out of the box faster and faster because they don't like to be confined. On the other hand, this is Edward Tolman, another very famous psychologist from the first part of the last century. And he was interested in the idea that animals, in fact, build sophisticated maps of their environment. This is just one of his experiments to look at that, which is called latent learning. So here, this is a task in which the animals are in an environment where there are basically a series of T mazes. They can go up here, they can turn right, they can turn left, and so forth. And they can move through this environment. Actually, topologically, it's just a single linear track with just single points of error. And what he then is looked at is three different groups of animals. In one group, they were regularly rewarded for going from the start box to the food box here. And you can see how many errors they're making. That's to say how many times they go down the wrong arm of the T. And you can see over progressive days, they do one trial a day, they get better and better and better, and they make fewer errors. You have another group which have no food rewards. They're just there existing in this maze, and they also run around. And you can still quantify their errors here with, of course, there's no external definition of error. They're just moving around. And you just say, how frequently do they go down these dead end arms of the T? And then you have a third group, which is just like the second group. So no reward until day 11. Then on day 11, those animals first find food in this food box. And then you can see that from day 12 onwards, they are actually even better than those animals that were regularly rewarded. And so what Tolman was observing is the idea that the animals here, this third group, they must have been learning something about the environment, such that then when it became important to use that information, they had this really embedded in the way that they could behave. So this idea that there are these multiple possible ways that we can understand the structure of learning in these animals is something which is then very richly embedded in psychology. This is a famous book from Daniel Kahneman, Thinking Fast and Slow. And the idea is that there's this Thorndikian system. It's sometimes called model free. You just learn, you do an action. If it's successful, then you just have a higher chance of repeating it. Whereas the model-based system is the system from Tolman, where you're building a model of the world and planning with that model. So they have different opposite characteristics. It's very fast to use the model-free system. You just learn this as a good action in this environment. But it's, on the other hand, it's sort of rigid because you don't have a representation of the environment that you're using to plan, which means if something changes, so we change some key aspect of that, you have to use a left rather than your right leg to move the lever, then even if you show the animal that, it's going to have to relearn in an expensive way. Whereas the model-based system is flexible. We saw that in the latent learning case when some information became important, like the goal, there was food available at one point in the environment. The animals were very fast to determine that. So we, about 10 years ago, developed a task which then tries to assess this in humans that we could look at. So the task runs a bit like this. There, you have to make two choices to have the chance of getting a reward. If you make the first choice, you have these between these two Tibetan characters, A and B. Then given, if you choose this one, then 70% of the time you get to the purple choice, 30% of the time you don't get a blue choice. Choose the other one, 70% of the time you get the blue choice, 30% of the time you get the purple choice. Then you make another choice at the second stage, whichever one of these two boxes you get to, and then you might or might not get a reward. And the logic of this task is that let's say you choose action A here, and you get to the unlikely outcome, to the blue box rather than the magenta box. And let's say you choose action C, and you get a big reward from that. Then next time I put you at this green box, do you choose A or B? So on one hand, you chose A, and in the end, you got a big reward. So that means maybe you should do A more. On the other hand, if you wanted to get to the blue box more with a higher probability, because that's where the reward came from, then you'd rather like to choose B instead. And so this task is trying to elicit this difference between the Thorndikean control, repeat A, and the model, the Tolmanian control, which would be to say, even though you got rewarded for A, do B next time. So one way of looking at that is to ask, with what probability do you repeat the action? So it's called a stay probability. And if you're a model-free, a Thorndikean controller, if you're rewarded, you have a higher chance of repeating it. If you're unrewarded, you have a lower chance. If you're a Tolmanian controller, now there's an interaction between whether you got reward and whether you had the common or the rare outcome. So here, this was the rare outcome, which means that even though you got reward, you should be less likely to repeat that same action the next time. And when you look at people, what you see is they mix these two things together in these two sorts of Thorndikean Tolmanian control. Then it's interesting to look at things like individual differences and their link to things like psychiatric disease. Okay, so there's been a huge wealth of work over the last 10 years and perhaps even beyond more, thinking about the way that these model-based and model-free systems might get integrated and how you might choose between them. So one is that we might choose based on how uncertain you are about the choices that each of them make. That uncertainty comes from learning and change. There's also work that maybe in even more complicated tasks, you might mix the values. So the Thorndikean controller is very fast to use. So maybe you can mix some Thorndikean values into this Tolmanian control. There are other ways that the model-based system can contribute to the way that control works. And then more recently, and this is something we've been very interested in over the last few years, is that the brain doesn't only have a possibility of training when you're actually experiencing actions in the world, but also that during periods of quiet restfulness and sleep, the brain, maybe the model-based system, can actually train the model-free system offline so that it expresses its knowledge and generates essentially what looks like a flexible model-free controller, which is nevertheless then fast to use in the context that is actually necessary. You could also have model-free choice of model-based goals. I haven't got time to talk about Nathaniel's lovely example from the wire of that. You can ask me a question about that afterwards. But what I want to do in this talk is to exploit a different task which Rani came up with, and also to look at another very key facet of the way that we think about control, which is confidence. So what we think about the probability of the correctness of the choices that we make, and how that interacts with this model-based and model-free controllers. So as I mentioned, confidence you can think of as being sort of subjective. It's the internal sense you have, a metacognitive sense of the probability that you took a correct action. And one of the there are many key findings in the world of confidence over the last few years. There's some very nice review paper by Steve Fleming and Nathaniel Dorr, which, for instance, talks about how confidence in decisions may rely on different sources of information. And the classic case here is what's called post-choice information, where the idea is you receive some information here about whether you should go left, let's say, or right. So you're receiving information which you're then integrating, and you have the idea is there's some sort of bound on this level of evidence about whether it's best to go left or right. And you make a decision. But before you can express the decision, because it takes you a while to move, you perhaps collect some extra information from the world, and you use this extra information to decide whether the choice you made was correct. So if the extra information is pointing in the same direction, you're more confident you're correct. If the extra information you get points in the opposite direction, then you become less confident, and maybe in the end you'd like to even change your mind. So one observation you might have is that if model-based calculations are slow, it takes you a long time to carry them out, then maybe model-based system when you're making choices online perhaps contributes more to the degree of confidence you have about a choice you make than it contributes to the choice itself. And that might vary by some metrics of the experiment that we have. The other thing you could say is in a task where you just have two choices, so you have a chosen option and an unchosen option, we can ask, is the degree of confidence associated in an absolute way, like the Q value, this is like something like the expected value of in this case, the action that you chose. If that's high, then maybe the choice you made, you think, I'm very confident that was a good idea. On the other hand, you could perhaps say, well, I'm interested in the choice between two actions. And so maybe something like the difference in the expected value. So the value of the chosen action minus your value of the unchosen action is something associated with the degree of confidence you have in the choice you made, rather than the degree of confidence that the choice was actually a good choice, absolutely. So this is like a relative measure, and this is instead an absolute measure. Okay, so here's the task that we did. I call it the meat and two veg task, you'll see why. So here the idea is a slightly different task than the one that Nathaniel designed. And at any time, you're going to have to choose between two of these people. So the person with the sunglasses, the boy, the lady, and the man with the beard. Each person, excuse me, is associated with two vegetables, although in fact neither the tomato nor the potato are really a vegetable, but we pretend that they are. And these vegetables are associated with rewards, and these rewards fluctuate over time. So here this is 60 trials. In the end, our subjects did 5 blocks of 60 trials each. And you can see that the probability that these veg are associated with the reward is moving in a random walk, something that the subjects can learn over time. And the fact that it's changing is why they need to learn in the first place. So the design of a trial here goes rather like this. So at any one time, so you have an intertrial interval of about a second. Subjects see the two people that they have to make a choice between on a trial. They have up to 2 seconds to make this decision. So here, the man with the sunglasses versus the boy. Then in this version of the task, having made that choice, they then have to rate their confidence in the choice. This is the metacognitive question that we asked. And then they say whether they think the choice they make is correct. Then over the next 2 or 2.5 seconds, they then see the person they chose. So here we know it's the person with the sunglasses. And then they showed in random order the two vegetables that person is associated with. So the guy with the sunglasses is associated with the tomato and the garlic. And you can see in this case, the tomato was rewarded and the garlic was not rewarded. Then they have a short break, they have another ITI, and then the next trial begins. And they have, let's say, 60 trials in a row. Okay, so how might we think the model-based and model-free systems, these Thorndikean and Tolmanian systems, might contribute to choice? So here the idea, and this is what's critical to the design of the task, is that the model-free system, the Thorndikean system, learns model-free values for people. The idea is a person is associated, so in this trial, the person, the guy with the sunglasses, is associated with the sum of the two rewards on this case. So it's just one, in this case, they got one reward associated with the tomato. They don't care about the association with the tomato. They just say, I chose this person, I got one reward. And so here, this is very standard delta learning rule or Q learning rule for the value of the person, which is some learning rate times how much reward, 1 in that case, minus the current value. On the other hand, the model-based system instead learns about the vegetables, right? It's the vegetables that are associated with the reward, the tomato and the garlic. So here we use the same learning rule, but now it's associated not with the person, but with the vegetable. And so that also learns how good that vegetable is over time, which is tracking that random walk. And now, if you want to decide what to do, then you can compute your model-based value by saying that this person, the guy with the sunglasses or the boy, is associated with the sum of the values of the two veg that that person is associated with. And so then that's how we learn about the veg, and then we use our model of the world, this very simple model, which is that the guy is associated with these two, the tomato and the garlic, to work out the value of that person in the end. Then it turns out that we can need a few little additions to the model. So of course, people forget over time. They also have a tendency to perseverate. They like to choose the same action they chose, the same person they chose in the previous case, or other people like to alternate, so choose a different person next time. And then when we compute the net value, as I mentioned very early on, we'd like to mix together the values of from the model-based system and the model-free system. And here we just have a weighting parameter, this W model-based, which says in this weighting, how much do we care about the model-based versus the model-free system? And we expect, based on other data, that this number is going to vary amongst individuals. And then this is the perseveration process, which says, are we going to favor the guy that we chose last time? And then typically in choice, we use a softmax choice or the sigmoid in the case you only have two possibilities, with some parameter beta, which says something about the slope of the sigmoid, an inverse temperature that says, if you have a small difference in the value of two people, how likely is it that you're going to choose that person? There's actually an error in that formula, sorry. Okay, so how can we understand model-free and model-based control in this very simple case? So let's first of all think about what a model-free effect looks like. So imagine on trial N, you had a choice between two people. You chose the guy with the sunglasses associated with the garlic and the tomato. And then on trial N+1, you're now faced with the same person, the guy with the sunglasses, and the boy. And critically, these two people share one outcome, the tomato, and they have one unique outcome, the garlic and the lettuce, I guess. Lettuce. So if you think it from a model-free perspective, from a model-based perspective, I'm sorry, from the structure of the task, the tomato is shared between the man with the sunglasses and the boy, which means that if on the trial N, this tomato was rewarded, from a model-based perspective, it should have no impact on the choice between the man with the sunglasses and the boy. But from a model-free perspective, you just learned on the basis of seeing this man with the sunglasses, you got a reward. So if you got a reward with the tomato, that means you're going to increase the value of the person with the sunglasses, and therefore be more likely to choose him on the next trial, if you're in trial n+1, if you're faced with him versus the boy. So the outcome of the tomato should boost your propensity to choose the man with the sunglasses next time. So here, what we're doing is we're comparing the effect of the unique vegetable. So did you get a reward on the garlic on this trial? That's this you none or you rewarded. So we certainly expect the probability of repeating the man with the sunglasses is going to be higher if the garlic was rewarded here, because the boy doesn't share the garlic, therefore it's not going to boost his value at all. And indeed, we see that there's a nice big effect where you're much more likely to repeat your action, choose the guy with the sunglasses again in this instance, if the unite was rewarded. But you also see that if the common item was rewarded, you're also more likely to choose that action, choose the same person again. And that is our signature of model-free control. So the pure model-based controller doesn't do that because the tomato is shared between them. So rewarding the tomato doesn't help you decide between the man with the sunglasses and the boy. The pure model-free controller has a stronger effect than we see in the data, and the full model, where we mix them together, then nicely captures what you see in the data themselves. Okay, how about the model-based system? How are we going to use this task to elicit that? So now we look again the same trial N with the man with the sunglasses and the garlic and the tomato. But now on trial N+1, we have the boy versus the guy with the beard, and these two share the lettuce. But now the boy has this unique tomato which it shares, whereas the guy with the beard instead has this potato. So now, if on this trial N, we rewarded the tomato, the model-based system is going to favor the boy rather than the man with the sunglasses, the man with the beard. But the model-free system doesn't use that information in any interesting way, because on this trial, the man with the sunglasses is not shown. So the fact that you've boosted the value of that person isn't going to help you decide between these two choices you have on trial N+1. So the guy with the boy is going to have an enhanced propensity to be chosen. So it turns out to be slightly subtle to prove that. So we prove that by, in this case, doing a sort of logistic regression. And here, the strength of the effect of the common reward, that's this the tomato, which is shared between the man with the sunglasses and the boy, that's our mark of model-based control, the strength of that in this particular way. Whereas this is just controlling for just the general propensity to choose the fact that tomato is highly rewarded. And what you see is that pure model-based control, again, has an even stronger effect along those lines. Pure model-free control doesn't have a significant effect of the common reward for the tomatoes, I argued, because you're not seeing the man with the sunglasses on that trial. Whereas, again, our full model, which contains a mixture of the two, does a good job of both the common reward effect and its property effect. This is the interaction between these two terms, and although there's a big variance, it's not significant. You can see it's not significant in the model too, but obviously there's a trend which is not completely matched in the data. When we compute a measure of model-based and model freeness, it's actually a slightly different measure than the WMB that I showed you before. It turns out they're essentially, roughly speaking, matched in our populations. There's no strong bias to one or the other. Okay, so that's how we make choices, how we distinguish model-based and model-free. What about confidence? So to assess this, what we did is we fit our choice model to the data. So the model I showed you, this full model, which does a good job. And then we wanted to understand who's contributing to confidence. And we can do that by running our model on the same choices and the same observations that the subjects got. And then that means we can ask from our model, we can ask what's the value of each of the people, what's the value of the choices you have, what's the model-based value, what's the model-free value. And also we have this perseverative tendency that I mentioned to repeat or to alternate. And we can ask those for both the chosen bandit and the rejected bandit, so the chosen person and the rejected person on any particular trial. And then we can look at the confidence ratings that our subjects gave, and we can regress them on a trial-by-trial basis with the 6 regresses we have. So for chosen and rejected times model-based, model-free, and perseveration. And here's what you see, which was a surprise to us, an interesting surprise. So from the model-based value, the person that was chosen has a very big effect on confidence, but the person who was unchosen has no effect on confidence at all. So this suggests that your model-based system is saying, is this an absolutely good choice or an absolutely bad choice? It doesn't care relative of that chosen versus unchosen. From a model-free perspective, we see something which has a weak positive value for the chosen one and a strong negative value for the unchosen one. So here, this is a more differential signal where you're comparing for the model-free, the chosen to the unchosen. But now you have a much stronger weight in the rejected case than the chosen case. And then there's an effect of perseveration on the rejected one. So here you're more confident, you have a particular sort of confidence associated with the unchosen bandit is associated with the perseveration. That's because of the way that you go about doing choice on those cases. And so another way of thinking about that is we can look at an asymmetry. So the contribution of the chosen versus unchosen value to boost or suppress confidence. And so for the model-based system, it's only the chosen value that matters. So chosen minus unchosen is very strong and positive. For the model-free values, instead it's the other way around. It's actually now more the unchosen value makes you less confident about the choice that you made. So then we can ask sort of measures of relative system contributions. And as you can guess from what I just showed you, that the model-based choice, which was fairly well matched across our subjects of model-free choice. On the other hand, the model-based contribution to the confidence for the chosen item is much stronger than the effect of the model based on choice. So we're measuring how much your choice is influenced by the model-based value, how much your confidence is influenced by the model-based value for the chosen item, for the chosen person. And so here you see it has a much stronger influence over confidence than it does over choice. On the other hand, for the confidence of the one that you rejected, the unchosen person, you can see that there's essentially almost no, as we saw before, there's almost no contribution of the model-based value of the unchosen person to the confidence that you express on that trial. Whereas again, the model-based system is, of course, still influential for choice. And now we can ask the relative contribution of the model-based confidence chosen to rejected. And again, we see that it's much stronger for the one which is chosen rather than one which is rejected. What we could also do is ask, instead of just looking in general about model-basedness, we can ask, we can split up model-basedness into what happens after a trial with high confidence or low confidence. You might think that if you had a trial with high confidence, then maybe you think, well, if things are going well, I can use my model-free system next because I don't have to think very hard. Whereas if you're only poorly confident, then maybe that's the time that you should think it's actually worth your while devoting a bit more cognitive control to those trials. And indeed, there's a weak effect, but significant effect nevertheless, which says that you're actually more model-based in the way you make choices after a low confidence trial. So there's an interaction between these systems, which I think is a really interesting interaction, which points in exactly the right direction. Okay, so let me sum up. So confidence here is dissociating the model-based and model-free systems. And it's actually in a way that we had not predicted originally. So you might think there'd be some sort of within system balance of evidence. We saw that the model-based system is not measuring chosen versus unchosen, it's just the chosen one. And we're not sort of down weighting the system based on the rejected bandit either. Doesn't look like they're controlling in that particular way. You could think of it as being consistent with a sort of selective post-choice integration. What I mean by that is, as I argued, the model-based system may be a bit slow to create its values, which means that the amount of influence it has over confidence could be much greater than the influence it has over choice, because that information is just filtering in as you're making those choices. But the asymmetries can lead to metacognitive inaccuracy. You're not correctly evaluating the confidence, the probably correct that you should have for the choices you have. In terms of ecological validity, though, why do it like this? One possibility that we've thought about is that imagine you have normally here we only have 2 options, but normally you have a very large number. So maybe it doesn't make sense to try and evaluate the difference between chosen and all these unchosen options you might have, or to work out in great detail the value of the second best option. So maybe what you do is you make a choice, and then the model-based system, if you have to make a confidence judgment, is there, and it's only looking at the one you chose and asking, is that a good choice? Absolutely, rather than asking in a relative manner. And we saw this very nice characteristic that the confidence is helping arbitrate between model-based and model-free in this rather particular way. So after a high confidence trial, you rely less on the model-based system because of its complexities. We've used other variants of this task. I haven't got time to tell you about them, but just to say very briefly some of the other things we've shown. So one is that the model-based system can control the way the model-free system updates its values by doing a sort of model-based inference about which of the vegetables was rewarded in a partial observation case, which means you don't see which vegetables they are. The model-based system has to infer what the vegetable was, and then the model-free system can then learn from that. We've shown the model-free system learning is controlled by a sort of relatedness. So we did a task where we provided counterfactual rewards. We told them told the subjects what the value of all the vegetables is, but then it turned out that it's only the vegetables that related to the model-free choice that you made contributed to the learning of that model-free system. And in fact, in that instance, so you have a choice between the guy with the sunglasses and the boy, then the potato isn't relevant to either of those two people, because the potato is in this context unique to the guy with the beard and the woman. And it turned out that this absent veg actually contributed negatively to the model-free value. So there's an interesting complex interaction of the way the model-based system helps the model-free system learn in these cases. And also the model-based learning was controlled by informativeness. So if on a trial you're faced between the man with the sunglasses and the boy, then the discriminative outcomes, the ones which actually matter for the model-based system, is the difference in value between the garlic and the lettuce, because that's the one which is unique. They both share the tomato. And it turned out that learning was boosted for those discriminative vegetables compared to the non-discriminative vegetables, the tomato. But remember, the model-based system should learn about all the vegetables equally, because they're all informative for subsequent choices. So this is another sort of non-normativity, which comes perhaps from a form of attention that there's been paid to the issue. So this is my last slide. So model-based, model-free is a really critical distinction in reinforcement learning, in economics, in psychology, and neuroscience. It really runs through like the lettering through a stick of rock in many, many different subjects, because it's just a very clear example of sort of dual systems. And then, but what we've seen is that in fact, it's not really two individual points. There's really a continuum, or perhaps many continua between these two. It's very interesting that the fields are now filling in many of these points on that continuum. It's not just isolated issues. There are really rich interactions over choice, over learning, the way that states are defined in this replay I mentioned, where the model-based system is training the model-free system offline. And then we've shown using these tasks that the model-based system has particular control over learning, the way that credit assignment works in the model-free system and also the model-based system, and then these notions of relatedness and informativeness too. So, and then what we also showed is there's this rich interaction between choice and confidence. And when you're thinking about the way these systems might trade off with each other, then one of the ideas is that uncertainty about the systems should control the way that you use one of the systems or the other to make choices. So we expected there to be an effect on a given trial of the relative certainty of these systems. It looks like, in fact, the effect is mostly on the next trial, which then speaks in an interesting way to the cognitive control mechanisms that the systems are using to make choices from one trial to the next. So plenty. Thank you very much.
Thank you, Peter. That was a really fascinating talk. I think we have time for about 2 questions from our panelists. I also remind people watching the webinar can put questions in the Q&A panel. So any inquiries from our panelists, other people? Georg, perhaps?
Yeah, hi, Peter. Thanks a lot for your talk. I was wondering and thought that the model-based part has also the chance to model the stochasticity of the environment, right? Or like of what could happen. So then this is a thing that the model-free algorithm cannot really do, because it can only compute expectations of what happened in the past, and it cannot really take all possibilities into account at the moment of decision and look at the full spectrum of the possible outcomes. Did you consider this, or can you maybe comment on this a bit?
Yeah, that's a great point. So there are 2 or 3 things to say. So one is that indeed you can, in other sorts of bandit tasks, you can often look to see if you can fit sort of Bayesian bandits and say, is the system, is a model-based system, so monitoring the uncertainties as it goes. And in these very simple systems, it's of course not that difficult to do, or at least to do a reasonable approximation by using a sort of forgetful bandit. And so it's really just a 2-parameter system. And in some cases, it didn't particularly fit so well in this particular case. In other cases, it has fit well. On the other hand, the model-free system can do something a little bit more sophisticated than I talked about. So when you think about the stochasticity, you're thinking about something like the rate of change of the world. So volatility, the reason why the model-free system has to learn is because things have changed. You start out ignorant and then things are changing, so you have ignorance thrust upon you. And so how fast you should learn should be controlled by the degree of volatility in the environment. And in fact, the brain has systems which seem to monitor the aspects of that volatility, probably in various different ways, and then control the rate of learning of the model-free system there. So in fact, the model-free system can be a bit more sophisticated than I talked about. And indeed, there's so many decades of work in psychology thinking about what controls the learning rates in these cases. And so we've used things like Kalman filter accounts to look at that. So then the other side of it is directed versus undirected exploration. So the model-based system can do much more sophisticated exploration based on the knowledge of its own uncertainty. That's not so important in these sorts of tasks, but people have shown in other, because the fact that these bandits are changing over time means you don't gain a huge amount by being really sophisticated in exploration. But people have shown in other tasks that the subjects do use something about the uncertainty to control the behavior. But what they haven't done is to try and dissociate the model-based and model-free components of that. So it'd be really nice to look at exploration, separating out model-based and model-free control and seeing if indeed both systems can contribute to the way that subjects explore.
Yeah, thank you very much. Very interesting.
Thank you for the nice question and the answer, Peter. Do we have a second question for Peter? Per, I see. Or
yeah, maybe if a naive question is allowed, because it seems to hinge on psychology, and to some extent, I mean, the model-free one is probably the naive learner or the young learner. And it seems to be also related to very high learning rates, whereas later on the rate slows down, but the sophistication increases. So does that explain something about human psychology?
So it's actually interesting to think about what controls the learning rates. As I argued just a minute ago, in fact, people and animals are quite good at adapting their learning rates to their ignorance. So how fast you should learn is a function of how fast the world changes when things, when you don't know. So obviously, when you're young, you should learn quickly because there are so many things you don't know. As you learn more and more, so things are less, in general, are less uncertain, then learning slows down, but it should slow down normatively unless you move into a new environment. And the brain has mechanisms which adapt to these new environments and thereby learn faster at that time. So it's certainly the case that we might expect a balance between model-based and model-free control to change over the course of the lifespan. You might think if you get really old, like me, your degree of model-based control, you might hope it goes up. In fact, it goes down, and it goes down associated actually with a decrease in probably in a dopamine system. So actually, we know something about the systems in the brain associated with that. We showed in other cases that we can then perhaps restore that using dopamine, by giving people dopamine, and that changes aspects of their behavior. So it's interesting to ask how we weigh the different sorts of controllers. But in terms of the learning rates themselves, I think that it's not quite the case that you should just be, when you're young, you should be fast, and when you're old, you should be slow. It's really a function of the way that you get to be ignorant in these cases.
Thank you, Peter. I'm going to suggest that we wrap up the questions, unless Bernhard, I think you have the privilege. If you would like to ask a question, please go ahead.
If there's still time.
We make time.
So maybe it's a brief one, or maybe Peter just chooses not to answer. Maybe it's a stupid question. So I know you're interested in computational psychiatry, and I was wondering if there's anything interesting to say about psychological disorders and how they relate to the interplay between model-based and model-free systems. Do you have any thoughts about that?
Actually, yes, there's a very active area of work in computational psychiatry. So there's work, for instance, by Claire Gillen looking at OCD, so obsessive compulsive disorder, showing that seems to be a disorder in which people have over-reliance on the model-free system rather than the model-based system. And of course, confidence is something which is really central to many different psychiatric diseases. The way you're, for instance, in something like psychosis, the way you become overconfident apparently about the sorts of choices you make. So again, we're very interested in looking at the interplay between these systems, the interplay on confidence, and then looking at that in diseases where they have an impact on the sorts of beliefs that people form and hold, and the sorts of choices they then make as well.
Super, thank you for the really interesting question. Let's all again thank Peter Dayan for his fascinating talk, and we're so happy to have him here in the Tübingen region. Now we're gonna shift a little bit and we're gonna stop the live stream and to move to our third scientific talk. So I need to